Problem 13. A vessel floating in dock water of RD 1.005 has the upper edge of the summer load line in the waterline to starboard and 50 millimeters above the waterline to port. If a freshwater allowance is 180 millimeters and TPC is 24, find the amount of cargo that the vessel can load to bring her to her permissible draft. Before we start, I would like to talk a little bit about our load lines. Our load lines, a ship's load lines, are physically found on the port and starboard side hulls. But the actual load lines that matter are not these two. The actual load lines that matter are virtual load lines that is found on the center line of the ship. That is found on the center line of the ship. Hence, whatever we see on our port and starboard side hulls is to be then virtually transferred to the load line, the imaginary load line, the virtual load line that is on the center line of the ship. Now, in the slide that you see on your right hand side, it is the view of the load lines on our port and starboard hulls as if seen from astern, and also assume that you can physically see those two load lines. Practically it is not possible, but imagine that you can actually see those two load lines on the physical load lines on the port and starboard side hulls. And you are watching the ship from astern, mind you. So I've just drawn this rectangle for you, and starting with the deck line, DL stands for the deck line. Then you have the tropical fresh load line, the fresh load line, tropical load line, summer load line, the winter load line, and if the ship has a winter North Atlantic load line, there will be a winter North Atlantic load line over here, and the rectangle will be extended still further down. I hope you have understood where the load line that matters is located. It is located on your center line. It is a virtual load line. So, coming back to the problem, it tells us that the upper edge of the summer load line is on the water line to starboard. So you see the S over here on the starboard side, summer, and the upper edge of that load line is on the water line. And it also tells us that on the port side it is 50 millimeters above the water line to port. The summer load line is 50 millimeters above the water line to the port side. Okay. Now, as I said earlier, what matters is the load line on the center line. So, on the for the load line on the center line, we have to take the sum or the difference of the two depending on where the load line is positioned with respect to the water line. On the starboard side, it is on the water line, and on the port side, it is 50 millimeters above the water line. Thus, the average is 50 plus 0 equal to 50 divided by 2 on the center line. Therefore, we have a summer load line is 25 millimeters above the water line. I would like to tell you something extra different Of course, you will learn this in the subsequent problems. If, okay, let me not fool around with this. I will just copy and paste it. If your water line was this, I will change the color to red. If your water line was this, and you saw that on your starboard side, your summer, your respective whatever the load line is above the water line, and on the port side also it is above the water line, then it is the sum of the two numbers divided by 2. So if on the port side it is 60 millimeters and starboard side it is 10 millimeters above the water line, it will be on the center line 60 plus 10 equal to 70 divided by 2, 35 millimeters above the water line on the center line. Now the same water line, if it was here, on one side your respective load line is below the water line, and on the other side the respective same load line is above the water line. In that case you have to take the difference. So let us say on the port side it is 60 millimeters above the water line and on the starboard side it is 20 millimeters below the water line. So on the center line it will be 60 minus 20 equal to 40 divided by 2 equal to 20. Now on the center line, will it be above the water line or below the water line is a very important thing to judge. That can easily be understood by taking the reference of the greater number. The greater number here is 60 millimeters, and that 60 millimeters says that your summer load line is above the water line. Hence, on the center line also it will be above the water line. And in this case, it will be 60 minus 20, that is 40 divided by 2 equal to 20 millimeters above the water line. So let us start with the solution of the problem now. The data given to us in the problem is this. On the starboard side, it is at the summer draft, that is at the top of the summer load line. On the port side, it is 50 millimeters above the water line. The mean freeboard at the center line is 0 plus 50 divided by 2 equal to 25 millimeters above the water line. We have been given freshwater allowance of 180 millimeters. Now, we know this is 25 millimeters above the water line at the center line. The summer load line is 25 millimeters above the water line. And we have to calculate the amount of cargo to load so that it will bring the vessel to her permissible draft. The permissible draft in this case is on your summer load line as given to us in the problem. Now we know that when she is in dock water 1.005 and she goes into salt water, her draft will reduce. Okay, she will rise. By how much she will rise is equal to the dock water allowance. And as we have seen earlier, that much extra can be taken into account to load her. If we do not take into account the dock water allowance, we are in effect underloading the ship, which is not permissible due to the economics. So you have to load her to the maximum possible capacity. Thus, we have to allow for the dock water allowance in these problems. So, we have to now calculate dock water allowance equal to freshwater allowance multiplied by the difference of two relative densities divided by 0.025. When we substitute the values, we have that equal to 144 millimeters. Therefore, the total sinkage now is equal to 25 millimeters plus 144 millimeters equal to 169 millimeters equal to 16.9 centimeters. Okay, total sinkage is equal to 16.9 centimeters. Now the TPC is 24, and that is the TPC in salt water, which has to be converted to TPC in dock water. The easiest and the fastest way to convert your TPC from salt water to dock water is to divide the TPC by the relative density of salt water 1.025 and multiply it by the relative density of the dock water, which in this case is 1.005. And you get that TPC equal to 23.53 metric tons per centimeter. Therefore, we have calculated the total sinkage and we have calculated the TPC in dock water. Therefore, the cargo to load is equal to sinkage multiplied by TPC. That is 16.9 multiplied by 23.53, giving us 397.7 metric tons. Now you may perhaps wonder as to how is this possible? Is there a way of cross-checking whether this number is correct or not? Yes, there is a way. We know that the formula for TPC is water plane area divided by 100 multiplied by relative density. Thus, water plane area in salt water can be easily found by TPC multiplied by 100 divided by the relative density of salt water equal to 2341.5 square meters. At the same draft, TPC in water plane area of salt water will be equal to the water plane area of dock water. TPC in dock water is equal to water plane area dock water divided by 100 multiplied by relative density of dock water. Thus we see TPC in dock water is equal to water plane area in dock water is 2341.5 square meters multiplied by relative density of the dock water 1.005 and divided by 100, and we get the answer to be 23.53 metric tons per centimeter, exactly the same. So in your exams you can easily and quickly work it out by this method instead of going up and using this long method. Problem 16. A vessel is lying in a river berth of density 1.010 metric tons per cubic meter with a summer load line 20 millimeters above the water on the starboard side and 50 millimeters above the water on the port side. Find how much cargo she can load to bring her to her summer load line in salt water if her summer displacement is 15,000 metric tons and TPC is 25 metric tons per centimeter. So once again, I've drawn the load lines for you, and as if viewed from astern, port side, starboard side, and these are your various load lines. What is given to us is that on the starboard side it is 20 millimeters above the water line. The summer load line is 20 millimeters above the water line. And on the port side it is 50 millimeters above the water line. As I explained to you earlier in the previous problem, when both sides are above the water line, you have to add the two numbers and divide by 2 to get the value of the summer load line, how many millimeters above the water line it will be on your center line. Thus we see 50 plus 20 divided by 2 equal to 35 millimeters. Thus on the center line, your summer load line is 35 millimeters above the water line. Now she is floating in 1.010 relative density, and you have to find how much cargo she can load to bring her to the summer load line in salt water. Now when she goes from dock water 1.010 to 1.025, the ship is going to rise by an amount equal to dock water allowance. Thus, this dock water allowance can be taken into account to load her extra when you are in the dock water in this problem 1.010. To find the dock water allowance, we first have to find her freshwater allowance. And we know the freshwater allowance is by formula is equal to displacement divided by 4 times the TPC, and the answer will be in millimeters. And the dock water allowance, the formula is freshwater allowance into the difference of two relative densities divided by 0.025. Once we have calculated that, of course, I have given you the values after the calculation. The freshwater allowance after calculation is 150 millimeters, and dock water allowance after I have calculated is 90 millimeters. Thus, we can have a sinkage allowance of 90 plus 35 equal to 125 millimeters. This multiplied by the dock water TPC. TPC that is given to us in the problem is 25 metric tons per centimeter. And as I have said earlier, it is always in salt water. This has to be converted to dock water TPC. And into dock water TPC, all we have to do is divide the salt water TPC by 1.025 and multiply it by the relative density of the dock water, which will give us 24.63 metric tons per centimeter. So let us start with the solution of the problem now. Given to us in the problem is this data. So the mean clearance is, add the two, divide the two equal to 35 millimeters. Why do we have to add the two? Because on both sides the summer load line is above the water level. So the mean clearance on the center line is equal to 35 millimeters. Freshwater allowance we know is equal to displacement divided by 4 times the TPC in salt water. When you put in the values, you get a freshwater allowance equal to 150 millimeters. From that we calculate dock water allowance. That is equal to freshwater allowance into the difference of two relative densities divided by 0.025. And we get dock water allowance equal to 90 millimeters, as I have shown over here in this slide. 90 millimeters is your dock water allowance, and the mean clearance on the center line is 35 millimeters. You add the two, you get 125 millimeters. That much sinkage is permissible. Now, 90 plus 35 is equal to 125 millimeters or 12.5 centimeters. TPC in salt water is 25 metric tons per centimeter. You convert that to TPC in dock water divided by 1.025 multiplied by the relative density of the dock water 1.010, and you get TPC in dock water equal to 24.63 metric tons per centimeter. Thus, the cargo to be loaded is equal to sinkage multiplied by TPC. Sinkage in centimeters 12.5, TPC in the dock water 24.63, giving us the cargo to be loaded equal to 307.9 metric tons. Problem 17 states, a vessel is floating in dock water of RD 1.005 with her starboard WNA mark 30 millimeters below and the port WNA mark 60 millimeters below the waterline. If her summer saltwater draft is 8.4 meters, TPC is 30 and freshwater allowance is 160 millimeters, calculate how much cargo can be loaded to bring the vessel to her summer draft in salt water. The data given to us in the problem is all of this, and that has been converted into this drawing. The WNA load line on the starboard side is 30 millimeters below the waterline, and on the port side it is below the waterline. Since the WNA load line is below the waterline on both port and starboard sides, the mean clearance on the center line is equal to the sum of the two clearances, that is in this case 60 plus 30 equal to 90, and divided by 2, that is equal to 45. So once again I repeat that the mean clearance on the center line of the WNA mark, since both sides it is below the water line, it will be the sum of the two divided by 2. That is, in this problem, 60 plus 30 divided by 2, that is equal to 45 millimeters. Now we also know that the distance, the height between the top of the winter load line and the top of the winter North Atlantic load line is equal to 50 millimeters. How much? It is equal to 50 millimeters. Thus, we have 50 minus 45 is equal to 5 millimeters. That is this clearance from the winter load line. 50 minus 45 equal to 5 millimeters. That is this clearance of the winter load line. The winter load line on the center line is 5 millimeters above the water line. Now, given to us in the problem is freshwater allowance 160 millimeters, TPC 30 metric tons per centimeter. We have to find the height between the summer and the winter load lines. To find the height between the summer and the winter load lines, we need to know the summer draft. And that is given to us in the problem as 0.4 meters. Thus, this height between the tops of the summer and winter load lines is equal to 1 by 48 of the summer draft in millimeters. So when you divide the summer draft by 48, you convert that summer draft into millimeters. 8.4 meters is equal to 8,400 millimeters divided by 48 equal to 175 millimeters. This is the height between the top of the summer load line and the top of the winter load line. We have to find how much cargo can be loaded to bring the vessel to her summer draft in salt water. Thus, we have to calculate the dock water allowance, which has to be added to the clearances. And we know freshwater allowance is equal to 160 millimeters. Therefore, dock water allowance can be calculated by using the formula freshwater allowance multiplied by the difference of relative densities divided by 0.025. Let us see the solution now. Summer draft given to us is 8.4 meters. Therefore, the distance between the summer and the winter load lines is 8,400 millimeters. Convert 8.4 meters into millimeters is 8,400 divided by 48, giving us a value of 175 millimeters, which I have shown over here. 175 millimeters. Distance between the winter and winter North Atlantic load lines we know is equal to 50 millimeters. Dock water allowance is given by the formula freshwater allowance into the difference of two relative densities divided by 0.025. When we put in the numbers, it is equal to 128 millimeters. We know that the winter North Atlantic mark below the waterline on port side is 60 millimeters and on the starboard side is 30 millimeters. Therefore, on the center line, it will be equal to 60 plus 30 divided by 2. The mean clearance of the WNA mark on the center line is equal to 45 millimeters. Therefore, the distance between the final water line and the WNA on the center line is equal to 128 plus 175 plus 50 minus 45. 128 plus 75 plus 50 minus 45. And that gives us equal to 308 millimeters or 30.8 centimeters. The TPC in salt water is converted to TPC in dock water and you get 29.42 metric tons per centimeter. Thus, the cargo that can be loaded to bring the vessel to her summer draft is equal to sinkage multiplied by TPC in dock water, that is 30.8 multiplied by 29.42, giving us a value of 905.8 metric tons. Problem 18. A vessel is loading in a saltwater dock and is lying with her starboard winter load line 60 millimeters above and her port winter load line 20 millimeters below the surface of the water. If her summer draft in salt water is 7.2 meters and the TPC is 20, find how many tons of cargo the vessel can load to bring her down to her tropical load line in salt water. Problem 18. The winter load line on the starboard side is 60 millimeters above the waterline and on the port side it is 20 millimeters below the waterline. Since both sides are not at the same point, one side is above and the other side is below, as I mentioned earlier, you have to take the difference of the two divided by 2. Thus, on the center line, the clearance of the winter load line will be 60 minus 20 divided by 2. That is equal to 20 millimeters. Now, you have to decide whether your winter load line will be above the water line or below the water line. And to help you decide, you have to look at the larger number. The larger number being 60 millimeters and it being 60 millimeters above the water line. Therefore, on the center line also it will be 20 millimeters above the water line. you see over here, the winter load line is 20 millimeters above the water line on the center line. Now we have to calculate how much will be the cargo that can be loaded to bring her to the tropical load line in salt water. To know how much is the clearance that you actually need on your center line from the water line to the tropical load line, you have to know your summer draft. And if you know your summer draft, you will be able to calculate the distances, the heights between your summer and winter load lines and tropical and summer load lines. Thus, we know that the summer draft given to us in the problem is 7.2 meters. 1 by 48 of that in millimeters is equal to 150 millimeters, and that is for both. Between tropical and summer is 150 millimeters, and between summer and winter is also 150 millimeters. Thus, we have a total clearance required of 150 plus 150 plus 20 equal to 320 millimeters equal to 32 centimeters. TPC given is 20 metric tons per centimeter, and she is in salt water. Okay, so since the TPC is in salt water and the ship is floating in salt water, we do not need to convert anything. We can straight away use that number of 20 metric tons per centimeter to get the amount of cargo that is required to bring the tropical load lines to the water line in salt water. So let us see the solution. Starboard winter load line 60 millimeters above the water line. Port winter load line 20 millimeters below the water line. Therefore, at the mean on the center line will be 20 millimeters above the water line. The summer draft given to us in the problem is 7.2 meters or 7,200 millimeters. Therefore, the distance between tropical load line and the winter load line is equal to the distance between tropical and summer and winter. In both cases, it is 1 by 48 of the summer draft. So, the distance between tropical and winter load lines is 1 by 48 of the summer draft multiplied by 2, which when you work out using the value of summer draft 7,200 millimeters, you get it equal to 300 millimeters or 30 centimeters. Thus, the total sinkage available to bring the vessel to the tropical load line is equal to 15 centimeters plus 15 centimeters plus 2 centimeters is equal to 32 centimeters. 150 millimeters is 15 centimeters plus another 15 centimeters plus another 2 centimeters. TPC given to us is in salt water and the ship is also floating in salt water, so we do not need to convert anything. We can straight away use the TPC as given to us, that is 20 metric tons per centimeter. Therefore, cargo to load is equal to TPC into sinkage. TPC is 20, sinkage is 32, and therefore the cargo to load is equal to 32 into 20 equal to 640 metric tons.